And to conceptualize the preburner of a Raptor 3, one must first appreciate the inherent chicken and egg paradox of high-performance rocketry. To generate the massive chamber pressures required for deep space transit, you need high-speed turbopumps. To drive those turbopumps, you need a high-energy gas source. And to get that high-energy gas source, you need ironically a rocket engine. And in a conventional automobile, the starter motor is a transient participant. It draws current from a battery, provides the initial torque to overcome the engine's static friction, and then gracefully disengages once the internal combustion cycle becomes self-sustaining. In the Raptor 3, the starter never leaves the stage. Instead, it evolves into the most critical subroutine in the entire stack. The preburners are, in essence, high-pressure chemical furnaces that act as the primary energy transducers for the vehicle. They take the raw chemical potential of liquid methane and liquid oxygen and convert it into the mechanical shaft power that keeps the heart of the engine beating. In the recursive architecture of power, for the software engineer, the preburner is best understood as a recursive function or a kernel-level subroutine. In a complex operating system, the kernel manages low-level hardware abstractions, memory allocation, CPU cycles, and I/O so that the user space applications can perform their tasks without worrying about the underlying physics of the silicon. In the preburner is the Raptor's kernel. The main combustion chamber, or MCC, is the user space application. It is the part of the engine that does the visible work of generating thrust. However, the MCC is entirely dependent on the preburners to stay scheduled. If the preburner fails to provide a consistent, high-pressure stream of gas to the turbines, the MCC starves, the pressure drops, and the system crashes. And this is recursive engineering because the preburner is, by every technical definition, a rocket engine in its own right. It has an injector head, a combustion zone, and a nozzle-like exit, though instead of venting to space, it vents into a turbine. It operates at pressures that would make the main engine of a 1960 rocket look like a toy. We are witnessing an engine whose sole purpose is to power the pumps of a larger engine. In the dual-kernel system, oxidizer-rich vs. fuel-rich, the Raptor 3 utilizes a full-flow staged combustion cycle, which necessitates not one, but two distinct preburners. This is where the complexity and the brilliance of the SpaceX design truly shines. And in most historical rocket engines, like the Space Shuttle main engine, designers chose one side to run the pumps. The Space Shuttle main engine used a fuel-rich cycle, where a small amount of oxygen was burned with a large amount of hydrogen. The resulting gas was hot enough to spin the turbines, but stayed cool enough not to melt the metal. The extra unburnt hydrogen then traveled into the main chamber to be finished. And the Raptor 3 rejects this compromise. It employs both an oxygen-rich preburner and a methane-rich preburner. In the oxygen-rich preburner, or the oxidizer-rich kernel, this unit takes the entire flow of liquid oxygen and mixes it with a tiny pilot-light amount of methane. The result is a high-pressure, high-temperature gas that is essentially superoxygen. The methane-rich preburner, or the fuel-rich kernel, this unit takes the entire flow of liquid methane and mixes it with a tiny amount of oxygen. The result is a hot, gaseous methane. And by running two separate preburners, SpaceX ensures that all the propellant entering the main combustion chamber is already in a gaseous state. In the world of thermodynamics, gas-gas combustion is orders of magnitude more efficient and stable than liquid-liquid or liquid-gas combustion. It is the difference between trying to light a log on fire with a match versus igniting a cloud of aerosolized gasoline. In power density, the suitcase-sized inferno. If you were to stand next to a Raptor No. 3 preburner, its physical scale would be profoundly deceiving. These units are roughly the size of a carry-on suitcase. Yet within that small volume, the engine is liberating energy at a rate that defies terrestrial comparison. And a single preburner on the Raptor No. 3 generates more horsepower than 20 Formula One cars combined. To achieve this, the mass flow rate, the amount of stuff moving through the chamber per second, is astronomical. The preburner is not just burning fuel, it is processing it at a velocity that approaches the limits of fluid dynamics. And the power density here is the critical metric. In a traditional power plant, a turbine capable of generating 100,000 horsepower would occupy a building the size of a warehouse. In the Raptor No. 3, that same power is packed into a space you could wrap your arms around. This density is required because every kilogram of engine is a kilogram of payload that cannot go to Mars. The preburner must be a concentrated, violent point of energy release, stripped of all unnecessary mass. In metallurgy, in the path of the dragon, the greatest challenge of the preburner is not the combustion itself, but the containment of that combustion. This is especially true for the oxygen-rich preburner. And in the history of metallurgy, oxygen-rich is a term synonymous with incendiary. At the pressures and temperatures found inside the ORPB, almost everything becomes fuel. Standard stainless steel will burn like a sparkler. Titanium will ignite with the ferocity of a thermite grenade. Even the most advanced nickel-based superalloys used in jet engines will oxidize and erode in seconds when exposed to a high-pressure, high-temperature oxygen stream. And to solve this, SpaceX had to develop a proprietary family of alloys known as the SX500 series. These are super-alloys, designed specifically to be chemically inert in the presence of angry oxygen. The internal walls of the preburner must maintain their structural integrity while being blasted by a gas that is actively trying to dissolve the metal's atomic bonds. And think of it as building a furnace out of wax, except the wax is a high-tech crystalline lattice of atoms specifically engineered to resist the solvency of the flame. If the material science fails by even a fraction of a percent, the result is a green flash, the signature of copper or other metals burning, followed by a catastrophic breach. The preburner would literally eat itself from the inside out. And the dynamics of the start, managing the latency. In computing, latency is the delay between a command and its execution. In the Raptor 3, the latency of the preburner start sequence is measured in milliseconds, and it is the most terrifying window of the entire flight profile. And to start the engine, you cannot simply turn it on. You have to choreograph a ballet of fluid dynamics. First, the pumps must be spun up by an external source, usually high-pressure nitrogen or helium. Then, a precise amount of methane and oxygen must be injected into the preburners and ignited. And if you inject too much fuel before the spark, you get a localized explosion that can shatter the turbine blades. If you inject too little, the flame can blow out, leading to a sudden loss of pressure that causes the main chamber to backflow into the turbopump. And the Raptor 3 manages this through a closed-loop control system that functions much like a high-frequency trading algorithm. Sensors inside the preburner monitor the pressure and temperature at kilohertz frequencies. If the flame front begins to waver or the pressure rises too quickly, the engine's flight computer adjusts the valve positions in real time to stabilize the subroutine. It is a constant, vibrating equilibrium, a controlled explosion that is always on the verge of becoming an uncontrolled one. And the acoustic nightmare, combustion instability. One of the most persistent ghosts in rocket engineering is combustion instability. When you burn fuel in a confined space at high pressure, the flame doesn't always burn smoothly. It can pulse. These pulses create sound waves. If the frequency of these sound waves matches the physical dimensions of the preburner chamber, you get resonance. And this is not the pleasant resonance of a violin string. This is screech or chugging acoustic oscillations, so violent they can shake the engine to pieces in a fraction of a second. Imagine a giant slamming a sledgehammer against the side of the engine 5,000 times per second. And the Raptor 3 preburners are designed with acoustic dampeners, tiny holes and baffles printed into the walls of the chamber that act like noise-canceling headphones. They absorb the energy of the pressure waves before they can build into a destructive resonance. This is another area where the 3D printing, or additive manufacturing, of the Raptor 3 is indispensable. These internal geometries are so complex they could never be machined or cast. They must be grown layer by layer to create the specific voids needed to silence the ghost in the machine. And integration, the preburner as a propellant preparer. While the preburner's primary job is to provide shaft power to the turbopumps, its secondary job is just as vital. It acts as a gasifier. And in a standard rocket, the fuel and oxidizer enter the main chamber as liquids. They have to atomize, mix, and ignite all within the few milliseconds they spend inside the chamber. This is incredibly difficult to do perfectly. And in the Raptor 3, because the preburners have already processed the propellant to spin the turbines, the fluids entering the main combustion chamber are already hot, high-pressure gases. The oxygen-rich preburner delivers hot oxygen. The methane-rich preburner delivers hot methane. When these two gaseous streams meet in the main injector, they don't need to be convinced to burn. They are already at the threshold of ignition. And this makes the main combustion chamber incredibly stable and efficient. The preburners have done the hard work of breaking the fluids down. By the time the propellant reaches the main event, the chemistry is a foregone conclusion. This is why the Raptor can achieve chamber pressures of 350 bar-a-feet, previously thought impossible for a production engine. It is not just about the strength of the walls, it is about the readiness of the gas. And the thermal gradient, a study in extremes. To appreciate the mechanical stress on the preburner, one must look at the thermal gradient. The inlet of the preburner is connected to the turbopump, which is filled with cryogenic liquid at minus 180 degrees Celsius. Just a few inches away, the combustion zone of the preburner is operating at temperatures exceeding 700 degrees Celsius, kept cool only by the massive excess of one propellant. And this means the metal of the preburner is experiencing a temperature delta of nearly 900 degrees over a distance shorter than a human hand. In any other machine, this would cause the metal to warp, crack, or creep, which means permanently deform. And the Raptor 3 manages this through regenerative cooling. Before the propellant is burned in the preburner, it is routed through tiny channels in the walls of the preburner itself. The cold liquid methane or oxygen acts as a coolant, soaking up the heat from the combustion and carrying it back into the flame. This not only keeps the metal from melting, but also preheats the fuel, recovering energy that would otherwise be wasted. It is a perfect thermodynamic loop, a closed system where every joule of energy is accounted for and recycled. And the invisible orchestra. If you were to watch a Raptor 3 static fire, you would hear a roar that sounds like the sky itself is being torn in half. Within that roar is an invisible orchestra of subsystems. The preburners are the percussion section, providing the rhythmic, high-energy drive that keeps the entire performance in sync. And they are the engines inside the engine, the recursive kernels of power that allow the Raptor to transcend the limits of 20th century rocketry. They represent the shift from brute force engineering to precision energy management. Without the preburner's ability to turn chemical potential into mechanical torque with surgical precision, the Starship would be nothing more than a very expensive lawn ornament. However, generating this much power is only half the battle. Once you have created these high-pressure, high-temperature gas streams, you have to control them. You have to ensure that exactly the right amount of superoxygen and hot methane reaches the main chamber at exactly the right microsecond. This requires a level of fluidic management that borders on the impossible. And to see how SpaceX tames this violent flow, we must look at the nervous system of the engine, the valves and sensors that translate the flight computer's intent into physical reality. In 3.4, managing the flow, valves, sensors, and real-time control.